Hi class, let's continue our discussion of infectious disease. We have talked about viruses and bacteria and spent a lot of time focusing on HIV, human immunodeficiency virus. We're going to pick up this discussion and focus on, starting off the block, tuberculosis. So what is tuberculosis? Tuberculosis is abbreviated as TB, and it's a infection that's caused by a bacterium known as Mycobacterium tuberculosis. Oftentimes it's referred to as that TB for tuberculosis, TB. It's estimated that approximately 1/3 of the total world's population has been exposed to TB. Now, that doesn't necessarily mean that 1/3 of the world's population has contracted TB. Whew, heaven forbid, that would be catastrophic. But we do have a lot of penetration of TB, particularly in developing countries. If we look at this on an annual basis, there's approximately 8.6 million people every year that are infected by this, and 1.3 million people that die every year from TB. So this is one of the big killers in our world. This disease is spread via aerosols or via the air. So when a person coughs or sneezes, they are going to emit small droplets that contain this tuberculosis bacterium. And this tuberculosis bacterium will travel through the small droplets and be inhaled, and the next person is exposed and may potentially develop the disease. Mycobacterium tuberculosis is notorious for having a very slow metabolic rate. And because it has a very slow metabolic rate, that means, first of all, that it can survive for a while within those aerosol droplets. And it also means that it grows very slowly within our bodies, and it responds very slowly to antibiotic treatments or antibiotic therapy. The likelihood of the tuberculosis bacterium causing an infection increases as you have more and more exposures. So just because we have 1/3 of the world's population exposed, that doesn't necessarily mean that 1/3 of the world's population is going to contract it every year. Most of those individuals don't have a high enough frequency of exposure to contract the infection. The incubation period, or how long it takes from contracting the disease to developing the symptoms, takes about 1 to 3 months, so 4 to 12 weeks. During this stage, this is the latent stage where you are incubating this disease, those TB individuals are going to not feel sick, but they are quite contagious. And we also have the active TB patients. These active TB patients are going to have symptoms, and they are also contagious at the same times. What are some of the symptoms of TB? Generally speaking, it's going to be coughing, hacking, having lots of sputum removed from the mouth, and as the disease progresses, some of the other symptoms become much more pronounced. But a key symptom of tuberculosis is hacking and coughing, which is also a key method of transmission of tuberculosis. So, how can we prevent and or treat tuberculosis? Well, right now, we typically are going to use antibiotics. That is the treatment method of choice. And there are going to be multiple antibiotic drugs given at the same time for 12 to 24 months. In other words, for up to at least a year, but up to 2 months. And why do we have to have such a prolonged therapy regimen? Because the virus has such a slow metabolism, and it's so difficult to remove this virus. There's also some key structures associated with how thick the waxy capsule is of this bacterium that makes it very difficult for us to destroy this bacterium. The drugs that are commonly given for tuberculosis infections include izoazid, rifampicin, ethambutol, and pyrazomide. Sorry, these are kind of tongue twister drugs for me here. Now, it doesn't necessarily mean, just because we have that 1 to 2 years of treatment, doesn't necessarily mean that the patient's going to be experiencing all the symptoms. They can start to have a reduction in symptoms in as little as 6 months. So it's going to take at least 6 months to start killing off the TB and kill off all of the TB. However, that's for the TB bacterium that, generally speaking, are going to be very active. There are going to be some TB bacterium that are in the dormant state, and these dormant TB bacterium take a much longer time to kill. Not only do they have a slow metabolism because they are TB bacterium, but they have an even slower metabolism because they're in their dormant state. So it takes forever, 1 to 2 years that is, for the antibiotics to fully destroy these TB bacterium. I should emphasize, though, that a major problem with this treatment treatment regimen is that many people cannot afford 12 to 24 months, 1 to 2 years of a daily antibiotic cocktail. So a major problem in developing countries right now is that patients will take some of the antibiotics, but not all of the antibiotics, and they will develop antibiotic resistant tuberculosis. And that is spreading rapidly right now in those developing countries. Moving on, we also have malaria. Malaria is a very, very common disease that affects over 200 million people a year. So if we assume that there are, let's say, 7.5 billion people on the planet, I'm doing some back-of-the-napkin math right now with my calculator. 200 million divided by 7.5 billion. This disease affects about 2.5% of the globe's population every single year, or 2.5% of all the people on the planet contract malaria every single year. Of those 200 million cases, there are going to be approximately 600,000 deaths from malaria every single year. Malaria is a unique disease in that it's not caused by bacteria, it's not caused by a virus or a prion, it's caused by a plasmodium, and this parasitic worm. And this parasitic worm is going to infect only humans. This plasmodium is transmitted by a specific kind of mosquito known as Anopheles gambiae. And this specific mosquito is going to transmit one of the 4 different plasmodium parasites into human beings. Why is this only transmitted by female mosquitoes? That's a question I often get from students. The reason is female mosquitoes are the egg-laying mosquitoes, and because they lay eggs, they need a source of protein in their diet. Only the females will suck up human blood. The male mosquitoes aren't attracted to humans to suck up their blood because they don't have the strong need for protein like the female mosquitoes do. So hence, we only are going to have female mosquitoes transmitting the disease. This disease of malaria has an incubation that's much, much shorter than tuberculosis. TB had that incubation period of 4 to 12 weeks. Malaria has an incubation period of 7 to 30 days, so significantly shorter. The symptoms can be very mild in some individuals or fatal in other individuals, particularly if somebody contains only one of the alleles for sickle cell anemia. So they're a heterozygote for sickle cell anemia. Those individuals will have mild symptoms. But if you don't have any of the alleles for the sickle cell gene, you are going to have much more pronounced, much more dramatic symptoms. The symptoms of this malarial disease include illness that is with flu-like symptoms and chills and fever. Generally speaking, these individuals feel terrible. And there's general malaise all over the place, all over their bodies, that is. Now, to prevent malaria, the best method of prevention is to avoid getting bitten by the mosquitoes. So we need to remove the mosquito populations by removing stagnant water, by using mosquito netting to keep the mosquitoes from coming in contact with us, by using mosquito spray to make our bodies less attractive to the mosquitoes. And you can also preemptively take anti-malarial drugs. 2 common anti-malarial drugs include quinone and artesunate. Quinone is the traditional antimalarial drug, and this quinone, or quinine, is an active ingredient in tonic water. This is why tonic water tastes so bitter. And it's also a primary reason why a gin and tonic is such a popular drink in British circles, or English culture. Back when England or Britain was a world empire, and Britain was colonizing or trying to establish footholds in tropical regions, the British troops or the British soldiers, since they didn't have that sickle cell anemia allele, they were very susceptible to malaria, and consequently they were taught or commanded to drink tonic water. But tonic water all by itself is terrible tasting. So to help make the strong taste of the quinone or the tonic water more palatable, they would mix it with a gin extract. And they came back to Britain, and they had learned to like the gin and tonic. It's an acquired taste like coffee and beer. And now it's still popular in certain British or English circles. I personally think a gin and tonic, or just tonic water in general, is not very good tasting. And we look globally, since malaria is associated with mosquitoes, we find that most malaria is going to be concentrated around the equator. So around tropical wet regions, there are going to be lots of individuals contracting malaria. In these purple areas, there's an increase in the prevalence of malaria. In the green areas, the darker the green is, the less, or the sharper the decline in malaria is going to be. And then finally, if the area on the globe is gray, there is either no malaria or there's no data concerning the amount of malaria because it's not applicable. The rates of malaria are so low. Our next infectious disease is influenza. Influenza is a disease that affects approximately 5 to 20% of Americans every year. Of that 5 or 20% of Americans, there's going to be about 36,000 fatalities every year. And if we assume that there are 300 million people in America, 36,000 comes out to less than 1% of the U.S. population dying from influenza every year. The infection rate, though, for influenza globally is unknown. Unfortunately, influenza is oftentimes misdiagnosed, which is one of the reasons why there's such a large fluctuation in this number, or variation in this number. The symptoms of influenza are very generic symptoms: runny nose, cough, chills, fever, head and body aches, nausea. These are super vague symptoms. And this virus that causes these symptoms is going to be transmitted via aerosol. So when somebody sneezes, they will emit small droplets of saliva that contain this virus. And sometimes someone can contract this disease by coming in physical contact with a contaminated object. So if you share a straw, if you share glassware, you can share this disease. Generally speaking, this virus is going to infect the cells of the respiratory tract. Those are the principal target cells for this virus. And we can have vaccine for influenza viruses. The downside of the influenza vaccine is that it only works against one strain of influenza. And there are many hundreds of different strains of influenza. And this virus is mutating very rapidly. So there's constantly new strains on the market. So just because you receive the influenza vaccine doesn't necessarily mean that you are going to be immune to all influenza viruses. It just means that you are immune to the specific strain of influenza the vaccine was designed for. Excuse me. One specific strain, H5N1, is a strain of influenza that's commonly referred to as the bird flu. If we look at the influenza virus, it's going to have two prominent spikes on its surface that it uses for docking. It has the H spike and the N spike, the heme agglutinin spike and the neuraminidase spike, hence the H and N nomenclature. The H spike is going to bind the virus to its host receptor, and the N spike is going to allow the virus to merge or attack the plasma membrane to get into the host cell. There are going to be small variations in the H spikes and the N spikes, hence the different numbers for the nomenclature system. So, like over here, we have H5N1. So this is the fifth structure for the H spike, and this particular strain had the first structure identified for the N spike, so we call it H5N1. Each of these different spikes is going to have different varieties or subtypes that have a specific number associated with them. Our immune system can only recognize a particular variety of H spikes and N spikes that it's been exposed to in the past. So every year, as you continually take this influenza, if you continually take the influenza vaccine every single year, you're exposing or immunizing yourself to a new strain of influenza. Eventually, you are going to be able to recognize more and more combinations of H spikes and N spikes so that you could theoretically be immune to more and more strains. So as we age, if we continually are exposing ourselves to this influenza vaccine, the rate of influenza should be on the decline in our bodies. If we look at a generic influenza virus, this generic virus is going to have both those H and N spikes that are going to be embedded within the viral envelope, and that viral envelope is a lipid-based envelope. But this virus has an RNA-based genome, so it has a very rapidly mutating genome. And a mutation can occur that will change the conformation of the shape of those surface spikes. And then another mutation can occur which will change the shape of an additional surface spike. So this influenza virus is constantly changing its appearance. Also, multiple host cells can be infected by different strains of the influenza virus. So we could have the same host cell be infected by a human flu virus and a bird flu virus. And if that occurs, let's say there's a small mutation in the host cell that makes it susceptible to both kinds of influenza viruses. In those situations, in that doubly infected host cell, viral genetic material can be mixed and matched, and we can have a brand new influenza virus. This is how we arrived with the bird flu or avian flu, because within a host cell, human influenza and bird or avian influenza mixed and matched with each other to come up with a brand new kind of influenza. So, class, what pathogen is concentrated in a tropical region? So, we are having a concept check right now, so you need to go ahead and rewind the video and check to see if you can find out which disease, which pathogen is located in tropical regions. If you don't know, that's okay. You can pause and check your notes. You can pause and check your textbook. Go ahead and get me an answer. 5, 4, 3, 2, 1. Malaria is concentrated within tropical regions on our globe. That is a disease that's typically associated with the tropics. Let's spend some time talking about emerging diseases. These are diseases that are on the rise, that haven't been around for a very long time. If we look at the NIAID list, or the National Institute of Allergy and Infectious Diseases database, emergent diseases are not the norm. These are new diseases on the block, and there are 18 pathogens that have been newly added or given or added to this list of emergent diseases within the last 20 years, one of which includes avian flu, H5N1, and we also have swine flu, which I remember back in 2012 was all over the Midwest, H1N1. And then we also have severe acute upper respiratory syndrome, or SARS, the SARS virus. Those are new diseases on the block. We also have re-emergent diseases. These are diseases that had been in significant decline, but now they're increasing again. For example, streptococcus is a re-emerging disease. We thought we had previously tackled or conquered that disease, but now as new antibiotic strains of streptococcal bacteria are being developed through natural selection, streptococcus is now re-emerging, becoming a new health problem or health hazard. Specific emerging disease that's covered in your text is Middle East Respiratory Syndrome, or MERS. This is formed by a coronavirus that's known to cause respiratory problems, hence the term respiratory syndrome. The animal host that is associated with MERS virus is unknown at this time, and it's been found that it can be transmitted by individuals that have close contact with each other. Generally speaking, if you're in close contact with somebody that's infected by this virus, there are going to be aerosols going from the infected person to you, the newly infected person. Infection by MERS is very dangerous, and the complications associated with MERS include things such as pneumonia and kidney failure. So it's not the MERS virus directly that causes the death, it's the complications associated with the MERS virus that are going to cause the mortality or fatality rates. Another huge issue facing our global healthcare system right now is antibiotic resistance. The very first antibiotic drug was discovered in 1943, and that's when penicillin hit the market. And within 4 years, the very first antibiotic-resistant bacteria were found. However, brand new strains or kinds of antibiotics were continually introduced for years and years and years, so we could keep ahead of the curve of the bacterial microevolution. However, it's been over 20 years since a new antibiotic has hit the market, so at this point in time, bacteria have had a lot of time to catch up and develop resistant genes and propagate these resistant strains throughout their populations. Antibiotic drugs used directly does not cause the humans to become resistant to the drugs. Instead, the bacteria that are attacked by the antibiotic are the ones that become resistant. The resistant strains of tuberculosis, for example, and Staphylococcus aureus are very concerning right now. The best way that we can fight antibiotic resistance, particularly, is to use antibiotics wisely. Don't overuse antibiotics, so things like antibiotic hand soap, that's a faux pas. That's a big no-no, because that's going to increase environmental antibiotic exposure to bacterial strains. But if you are sick and you're prescribed a regimen of antibiotics by your physician, you should take all of those antibiotics the physician has prescribed to you. Particularly if we look at the Staphylococcus aureus and TB strains. Methicillin-resistant Staphylococcus aureus is known as MRSA, and MRSA is currently a major problem within Midwest healthcare systems right now. Antibiotic-resistant tuberculosis is more of a developing country problem, but it's starting to make its way into the United States. On that note of antibiotic-resistant tuberculosis, there's sometimes in the literature you'll see X-resistant or XTB, and those strains of tuberculosis are resistant to all known antibiotics. They're sometimes referred to as pan-resistant tuberculosis. And these pan-resistant strains of tuberculosis are currently working their way through sub-Saharan Africa and currently working their way through the Russian prison system. And it's terrifying because these strains of tuberculosis do not have any known antibiotic cure and have very high fatality rates. How does antibiotic resistance develop? Well, you typically are going to start off with many millions or billions of bacterium. And just through general mutations, a couple of those bacteria, not many, just a few, will have a drug-resistant gene that's been mutated or formed. And if you have a low dose of antibiotics, you'll kill off the susceptible bacteria, but the resistant bacteria are not killed off by that low dose of antibiotics, and they can survive and repopulate as a resistant strain of antibiotics. As an antibiotic-resistant strain of bacteria. So the moral of the story is, if you minimize your antibiotic exposure to the bacteria, these resistant strains are not going to preferentially fill up the population. And another moral of the story is, if you have to take an antibiotic regimen, you should take the entire regimen of antibiotics, because extremely high doses of antibiotic can kill off a resistant strain, but only if that resistant strain is exposed to the very high doses of antibiotic very early on. So, class, concept checked. What is the danger of antibiotic-resistant bacteria? Is it A, that we do not have many more antibiotics to use, B, they are very difficult to kill, C, they are spreading rapidly, or D, all of the above? Go ahead and rewind the video and double check to get me an answer, or you can check your text or your printed notes. Go ahead and get me an answer right now. 5, 4, 3, 2, 1. Okie dokie. The correct answer is D, all of the above. Antibiotic-resistant bacteria are currently spreading very rapidly throughout the world. They're very difficult to kill because they are resistant to the preferred method of destroying them. And then finally, they are dangerous because we haven't had new antibiotics hit the market for a very long time now, over 20 years. And that's all we have for our chapter discussion. If you need help